Dear respected AASPI sponsors, welcome to my first presentation, a comprehensive comparison of generating seismic fault attributes using deep learning. My name is Bo Zhang from the University of Alabama. Here is my presentation outline. First, I would like to show the procedures of seismic fault attributes computed using deep learning. In these slides, I show a typical workflow of compute seismic fault attributes using deep learning. The input is a 3D seismic data and also the corresponding labels. Here, the deep learning I'm using the CNN, the architecture is ULET. The output is a model. The model can predict the seismic fault location with label 1. The strong seismic fault location is labeled as 0. Spatial continuity is the main advantages for the seismic fault attributes computed using deep learning. In these slides, the left figure shows a seismic section. The right figure shows the seismic section overlaid with seismic coherence attributes. Please note that the seismic coherence attributes lack of spatial continuity, although the seismic coherence attributes can highlight the location of the seismic faults. In these slides, I show the same seismic section and the seismic section overlaid with seismic fault attributes computed using deep learning. Please note that the seismic fault attributes has improved spatial continuity. To produce the seismic fault attributes, we need to train a model. In this example, the input training data is 200 3D seismic cubes. The size of each seismic cube is 128 samples by 128 samples by 128 samples. Note that we have a better spatial continuity when compared to the seismic coherence attributes. But the disadvantage is also obvious. For example, here, the seismic fault attributes computed from deep learning fails to highlight the fault indicated by the red arrow. And here is the artifacts produced by the deep learning. Those artifacts is linked with some stratigraphy boundaries. Please note that the training data is synthetic data. The real world is much complex than the synthetic model. So we can conclude that the training data lacks of generalizability. A lot of researchers find some ways to improve the accuracy of predicted faults. Trying the cutting-edge deep learning algorithms is one option. In these slides, I show one of the cutting-edge deep learning algorithms. The name of these deep learning algorithms is named as holistically listed ULET. In abbreviation, I named it as HULET. Compared to the traditional ULET, the HULET will output the predicted result at each of the architecture or each level, the cost function will not only compare the predicted results and the ground truth, it will also compare the predicted result at each level with the ground truth at each level. As a result, the H unit realizes multiple scale, multiple resolution results. In these slides, I show the predicted results using the H unit. If I compare this result with the result computed from the unit, the improvement is obvious. For example, here, the H unit successfully located at the fourth location, but at the same time, we still have some noise or artifacts. So as I mentioned before, the real world is complex. Synthetic data will not always working, even we have revised method. In these slides, the fault attributes is overlaid with seismic data. The training data to produce the H unit is synthetic data. It is obvious that this is not a good product for seismic interpreters. For example, here and here, the fault attributes is linked with the sequence boundaries. There are other ways to improve the accuracy of the seismic or fault attributes. Data augmentation and ensembling learning is another option. So the common data augmentation include cropping, left-right rotation, upside-down rotation, and additional noise. So in this slide, I show the predicted results using different data augmentation. And here, this figure is the original seismic data, and this is the predicted result using training data. There is low data augmentation, and this figure is the predicted results after cropping the training data, and then interpolating the training data. And this result is the upside down flip of the training data, and this result is the upside down left-right rotation data. And here, the last figure is the result after I add additional noise to the training data. After I perform data augmentation to the training data, the next step is ensemble learning. The ensemble learning will produce voting weights from different data augmentation. The input is the training data. Then I'm going to crop the seismic data and produced number 1. And the original seismic data produced number 2. And the flipped data produced number 3. Rotated data produced result number 5. And other additional noise, I'm going to produce result number 6. Then I'm going to apply ensemble learning to the 6 different results and have my final output. In these slides, the left figure shows the result computed using H unit. The right figure shows the result computed using ensemble learning. It is obvious that the spatial continuity is improved, and at the same time, the resolution is improved due to the data augmentation and the ensemble learning. However, we still have some artifacts. For example, here and here. So here is another example using ensemble learning. You can notice that we have a lot of horizontal anomalies. Those horizontal anomalies are definitely not the location of seismic fault. So these slides, together with previous slides, illustrate that synthetic data is too simple for the real world. As I mentioned before, the real world is complex. It is impossible to produce synthetic data that is exactly the same with real seismic data. Thus, I argue that we didn't include some information from their real seismic data. Unfortunately, to produce 3D seismic data from real seismic data is not realistic. Especially consider the training data. The size of the training data is 128 by 128 by 128. So it is a good choice to start with a 2D synthetic training data. In these slides, I generated 20,000 2D synthetic data. And here is the result after I applied a 2D model to the real seismic data. Of course, the result is unacceptable. The seismic fault attributes only highlight some of the fault location. However, it is a good start point. Next, I have a fresh interpreter to interpret 6 vertex sections within the seismic survey. The fresh interpreter has low previous interpretation experience. It takes him about 30 minutes to produce such 6 sections. In these slides, I illustrated one seismic section and the corresponding interpreted results. You guys can notice that the seismic fault location is highlighted by purple color. Then the seismic interpreted seismic data is added into the training data. The left image shows a seismic section at the middle of 2 interpreted seismic sections, which means there is low interpretation on this seismic section. The right image shows the predicted result. Note that the results are superior to any of previous results. The accuracy, spatial continuity, and resolution are all improved. Although we have some artifacts at the base of the images. To better see the improvement, I display all results in the same image. The first image is a 3D unit. The training data is synthetic 3D seismic cube. The second image is from the 3D H unit. The training data again is synthetic 3D seismic cube. The third figure is the result from ensemble learning. The training data is 3D synthetic seismic cube. Figure number 1, number 2, and number 3, I use the same training data. The 3D seismic data consists of 200 cubes, which is produced by Dr. Wu. The last image is a 2D ensemble learning results plus the training part of the training data is synthetic. Part of the training data is manually interpreted results. If we compare those four images, it is obvious that the 2D ensemble learning plus the interpreter information is the best one. To further demonstrate the effectiveness, I compare results for another scientific survey. For this scientific survey, the manual interpreted grade is 200 by 300. That means we will have one interpreted scientific section every 200 inlines and every 300 cross lines. The upper left image is original scientific data. The upper right image is a 3D predicted result using 3D unit. The lower left image is a predicted result using 3D ensemble learning, and the lower right image is a result using 2D unit plus interpreter's information. It is obvious that the 2D unit plus interpreter information is superior than other results. Based on the testing, I'm going to draw the following conclusions. Deep learning is a promising method to produce seismic fault attributes with better spatial continuity. The cutting-edge deep learning methods, data augmentation, and ensemble learning help to improve the quality of seismic attributes. However, we strongly argue that the information from interpreters is highly above the top of the pyramid of deep learning, which means we should include information from the real seismic data in the deep learning. Considering the difficulty to produce a 3D training data from real seismic data, we suggest 2D deep learning will be a better choice in produce the seismic fault attributes. This is the end of my first presentation. Now I'm ready to take any questions. Thank you all.